Howdy. So while we're waiting, I'll show you guys what I've been doing. I was just in my backyard and I was cutting some steel. So I got so I had a piece for Mr. Tucker. It's like a rectangular piece like this. Okay. And so I cut these two pieces off the side to make this. Okay. And so this is going to be my brother's Christmas present. I'm going to forge this. So this, it's, maybe 6 inches long. That's not long enough for the handle of an axe, but this is pretty thick. So I'm going to thin this out, make this thinner, and make it narrower. And I should be able to draw it out to about here maybe, so that it's an axe handle. Then I'm going to forge this down into a blade, or for a double-sided axe. So, because when my brother came to visit me over Thanksgiving, he was really into my axe throwing target. So he's going to have not just one side, but two sides, two-bladed axe. Then, with these other pieces, these are pretty much identical. I'm going to forge a matching pair of throwing knives. My dad doesn't throw knives. I've never tried it before, but I want to. So I think it's going to be cool. Then, with the steel scraps, I've been working on trying to make jewelry out of the steel scraps. So I have all these little triangular pieces. So I took them and I polished them and made little like jewelry. So I think that looks kind of cool. I don't know if I can get it to reflect the light, but it's pretty shiny. So that is going to be the gift for the ladies in my family. So I'm actually going to make a earrings as well. So like maybe an earring out of it. What do you think? Give me feedback. Come on, people. All right. So, let's go ahead and get started. Give the women knives too. Okay. So yeah, this is going to be a really quick lesson. So this lesson is kind of a callback. So back when we discussed energy, I forgot to talk about power. So that is the topic of today's lesson. There's a question. What made me choose a metal handle over a wood one for the axe? Okay, that's a really good question. That's why I'm going to answer it. So if you have an axe that has a wooden handle, the wooden handle goes through the axe. What you do is you have the axe head, you drive a wooden handle through it, and then once it's poking out the other side, you take another piece of wood and you, like a wedge, and you wedge it in there so that the wood widens at the top, and so it can't fall back out. It is very difficult to poke a hole in the steel, especially steel this thin, for the axe handle to go through. I would need to like drill it and then widen it, which means I would need a drill bit this long, and then I would need some kind of a punch, and it would just be a huge pain. So that's why it's not that's why it's a metal handle. That's a good question. Basically, it's hard to fabricate a hole with my equipment. I've gone through so many drill bits trying to drill steel. It's like 20, 30 drill bits, trying to drill steel. Like even this this necklace, I was having such a hard time drilling. You guys can't see that. So the back, it's soldered on. So if you look at the back, the chain is soldered onto the back. Now, ideally, I would like to drill through so that the chain can just go through the center, but it's such a pain to drill steel that I think I just don't have the right drill press. My drill bits aren't very high quality, so. But I'm just an amateur, so I'm not willing to spend tons and tons of money at this point in time on getting the best equipment. Okay, so at any rate, today's lesson is going to be about power. And this is going to go with Energy Quiz 4. So it's in a different module. It's kind of out of order. Okay. So what is power? Well, power is the rate at which work is done. So it's the derivative of the work with respect to time. The units of power are quite easy to determine from this definition. Well, it's work per time. So work is measured in joules, time is measured in seconds. So that is the watt W. Okay. 1 joule per second is defined as 1 watt W. So here's what we're going to do. We're going to take the definition of work. So I gave you actually 2 definitions of work. One of them was from the last lesson. Work was the integral of force with respect to position. Or if we're talking about rotational work, work was equal to the integral of torque with respect to angle. All right. So I'm going to do a little tricky trick. I'm going to multiply this by 1, but I'm going to multiply it by 1 written in a weird way. I'm going to multiply it by dt over dt. So dt over dt, they just cancel out, and I get back to where I started. So again, on this one, I'm going to multiply by dt, and I'm going to divide by dt. All right. Okay, because I want to take the derivative of this with respect to time, so I better put it in terms of time. Derivative of position with respect to time is velocity. So force times velocity, dt. And here, the derivative of angle with respect to time is the angular velocity. Okay. So now what we'll do is I will take the derivative with respect to time, and I'm going to use the fundamental theorem of calculus. So if you take the derivative, okay, so if you have something like I equals the integral of g of t with respect to time, and I take the derivative with respect to time, that just gets me back to my original function. So the derivative undoes the integral. I think that's the fundamental theorem of calculus. So when we do that, I take the derivative of the work with respect to time, I get rid of the integral, and I just get force times velocity. Okay. Over here, I take the derivative with respect to time, and I get rid of the integral, and I get torque times angular velocity. Okay? So these equations are correct. There's a three-dimensional version of this equation. If you have forces that are acting three-dimensionally and velocities in 3 dimensions, where this is the dot product. So the dot product of force with velocity is the power. And the rotational power is torque times angular velocity. Okay? So maybe I should leave that for a second. So what we're going to do for the remainder of class is just kind of play around with these two equations. The quiz for today is really short, so it shouldn't be too bad. So let's talk about, as an example, let's talk about an airplane. So when an airplane is flying, it has 4 forces acting on it. It's got the force of lift. It's got the weight force. It's got the force of thrust. And it's got the drag force. And so the drag force in previous lessons was CV, minus CV. But here, actually for an airplane, it's more appropriate to use the equation CV squared. So CV squared is the drag force. Okay? Now, if the plane is in level flight, okay, if we have level flight, then lift has to match weight. Those two are going to balance each other. If we have level flight at a constant velocity, then the thrust has to be balanced by the drag force. So we have 2 forces that are balancing each other out, 2 pairs of forces, and each pair is canceling the other, is canceling each other out. Okay? So in particular, we have, because the thrust has to be equal to the drag force, we have to have thrust equals CV squared. And important point, this is only if the airplane is flying at a constant velocity. If thrust is bigger than drag, it's going to accelerate. If thrust is smaller than drag, it's going to slow down. Okay? So based on this, we can actually deduce the power output of the engine. So the power output of the engine is going to be thrust times velocity. Okay? And we know that if the airplane is traveling at a constant velocity, then the thrust is CV squared. So we have CV squared times V, which is CV cubed. So this is the power output of the engine. And what this says, and I think this is really interesting, is what it says is that the faster the airplane is going, the more the power output of the engine. And it's a pretty dramatic increase. It increases as the cube of the speed, okay? So if an airplane doubles its speed, that double gets cubed, and so you actually get 8 times the speed, or 8 times the power, excuse me. Okay? So what does an airplane do? Because the engine is obviously limited in how much power it can supply, right? So, so what that means is that because the power output of the airplane engine is constrained to some maximum value, what the airplane will do if it wants to go faster is it will climb in altitude. And when it climbs in altitude, it goes to a place where the air is thinner and the drag coefficient is lower. So I think that's interesting. I got a question for you. Who knows what the fastest airplane or fastest jet humans have ever made is? Okay, there's a good question in the chat, which is, can you explain why you would use CV squared in terms of CV? Well, the minus sign is already taken into account with just the fact that this is in the opposite direction. But drag is a very, it's complicated. How drag behaves is really complicated. And it turns out that CV squared is more appropriate for human-sized objects moving at human-sized speeds, okay? Whereas CV is more appropriate for really tiny things like microbes and, you know, so it depends on the size. So the thing you have to understand is that our formula for drag force is modeling what we observe in nature. So it's not that the formula that nature has to obey the formula; it's that the formula has to obey nature, and so yeah. So this is the form that most closely obeys nature for an airplane. Yeah. So it's the SR-71 Blackbird. Goes Mach 3, or it went Mach 3. I don't think it's in service anymore. I used to be obsessed with the SR-71 Blackbird. I had a giant poster of it in my room. It's a beautiful airplane. I've seen it take off. I've seen it land. It's pretty cool. It's all black with red stripes on it. And it goes Mach 3. The reason it can go so fast is because it climbs, it's almost in outer space, right? It's using oxygen to combust its fuel from the air, but it's so high up that the air is really thin and it can go really, really, really fast. It's a spy plane. It had cameras on it that would take pictures. If anyone launched a missile at the SR-71 Blackbird, it was so high up that it could see the missile coming, and then it would just accelerate, and it would just beat the missile. So, yeah, so the difference between rockets can go much faster than that, but rockets are not jets. A jet is taking in oxygen from the air and combusting fuel with that oxygen, whereas a rocket does not require any oxygen from the air in order to. So basically, a rocket, you bring your own oxygen so it can work in outer space. That's pretty cool. All right. So let's do another example. You lift a mass m, a distance d, with a force F. So you're just lifting weights. You lift the weight up a certain distance by applying a certain force. What is the average power output? Okay. What is the average power output? So the reason I say average power output is because when you are applying a force on something and lifting up, if the force you're applying is greater than the weight force, then the object is going to accelerate upward. Okay? It's going to accelerate upward. And so its velocity is not going to be constant, and so the power is not going to be constant. So when we're computing average power, I'll use F times the average velocity. Okay? So if we're thinking about this if we're thinking about this situation, I'll draw a free body diagram. We got a force F, that's an applied force from your muscles. And we've got a downward force mg. Okay, so doing Newton's second law, net force equals ma. The net force is F minus mg. Okay, and then, so what that says is that the acceleration is equal to, dividing both sides by m, I get F over m minus g is the acceleration. All right? So now I'm going to do kinematics to figure out what the average velocity is. So I'm going to use that kinematics equation, delta x equals 1/2 at squared. So in using this equation, I'm assuming that that it starts at rest, because there's no v naught term. The distance that it travels is d, and the acceleration is F over m minus g. So based on this, I can calculate the time, okay? So the time in order to lift it, okay? So this gives me t equals 2d over F over m minus g square root. All right? So then, based on that, I can calculate the average velocity. The average velocity is going to be distance traveled divided by time it took. So that's going to be d over square root of 2d over F over m minus g. Okay. Simplifying that, it equals d over 2 times F over m minus g square root. Okay. And then to get the average power, I would take F and multiply it with the average velocity. So I have F times the quantity, d over 2 times the quantity F over m minus g. Okay? So basically what this equation says is the bigger the force you apply, the larger your power output. Okay? Which makes sense. So oftentimes what happens is you calculate the power, and the power depends on some variable. I'm going to call that variable psi. All right? So there's just some variable. It could be, this variable could be anything. It could be the mass of the power of the thing that you're lifting. It could be the force that you apply. It could be the, the RPM of the engine. It could be anything. It's just the power depends on some variable. Okay? And what we often want to do in engineering is we want to maximize the power. Okay? We want to maximize the power because we want to get as much as possible out of this thing. So what we would do is we would set the derivative of the power with respect to that variable equal to 0. Okay? And that would allow us to find the maximum power. Okay? So it helps our design. So we want the maximum power from our devices, and so we figure out what are the design parameters that are going to give us the greatest possible power. Okay. So this is used a lot in engineering. For example, when if we're talking about an engine, or let's say an engine. Engines have an optimal RPM for their power output. Okay, so there's an RPM for the engine where it outputs its maximum power. Okay, and so what you want to do is you can change the gear of the engine, okay, until you're at the gear that has it at the optimal RPM. Same thing with bicycles. When you're pedaling, there's a certain rate of pedaling at which you have the maximum power output that you can do. Okay? And so you set the gear on the pedals so that you are pedaling at that optimum rate. And we do that naturally. Okay? We don't even have to think about it. But really what you're doing when you're changing the gears as you're riding the bike is you're making sure that you're outputting as much power as possible for a given effort level. Okay? So like if you say, I'm not going to try very hard, I'm just going to have a relaxed bike ride, then for your relaxed bike ride, there is a certain pedal rate that is best, that will get you the most power for that amount of effort, okay? And it might be different from if you are going all out, okay? So same thing with engines, it's like you're pressing the gas down a certain amount. If you press the gas down more, the engine is going to give you more power up to a certain point, okay? But for a given amount of I'm pressing the gas pedal down this much, there's an optimal RPM for the engine, okay? So that's my lesson for today, so I will see you